So that's what's coming next. I'm just going to scroll this down to the next diagram that looks just like that one. There it is. These figures look so strikingly similar that you'll get confused if I don't point out the difference. This is the extended Kalman filter, which differs from the Kalman filter in that the Kalman filter came out first, and this was back in the days when nobody wanted to deal with nonlinear functions, and so we assumed everything was linear. And then later on, people decided, hey, wouldn't it be cool if we could do this with nonlinear functions? And that's kind of important because a lot of things in the real world are nonlinear. And this is very similar to the Kalman filter. So similar, in fact, that if you understood the previous one, this one's going to just make a lot of sense. Let's just do that now. So you're going to feed in x and p, same thing. We're using multivariate normal distributions to estimate where your state is. That's going to go in the new state, x hat minus sub k. So the hat means it's an estimate. The minus, I think, means we're not done computing it yet because we're going to adjust it over here. See how x without the minus is computed from x with the minus. So the minus just means not yet final. Okay. X is a function of the old x and the controls that you put in. So we finally combined the transitions and the controls into one function here. And I think that makes, to me, that makes even more sense. But you have to combine them because we're nonlinear now. And it may be that your controls have more effect in some regions of the state space than they do in other regions of the state space. For example, if you fire a rocket straight down, your rocket's going to go straight up, whereas if your rocket is pointed sideways, firing it sideways doesn't have the same effect on it or something like that. Okay, bad example. But x is a function of u. This looks about the same, I think. We'll talk about where some of these matrices come from in a minute, but you're still computing a Kalman gain. You're still updating your state based on the difference between your anticipated observation and your actual observation. Big difference here is now we're using a function instead of a matrix to compute our observation. So what we observe is a function of our state. And then we update our covariance again. And that's it. So there's the extended Kalman filter.
The matrix H.
Yep. So now there's a big H right there, and here's a little h, which is a function. And we need to talk about something called the Jacobian.
Oh,
Yeah, it's a Jacobian. Sorry, I should have given the straight answer first, rather than the condescending answer. But yes, here it is. The computational origins of the filter. There's a nice table here. A is the Jacobian matrix of partial derivatives of f with respect to x. W is the Jacobian matrix of partial derivatives of f with respect to w. X hat sub k is a posterior estimate of the states of step k. So all your questions are answered right here. Nevertheless, I'd like to try to answer them for you too, so that when you read through this, you have some context to give you basis for reading it. Let's talk about it like this. I'm going to draw my standard manifold because it's the only manifold I know how to draw. Pretend you have a surface in high-dimensional space, and the surface is nonlinear. Pretty clear that's not a plane, right? Now, at any single point on here, you could, if you wanted to, compute the tangent plane. Pretend that grid represents a patch that is incidental to this manifold. So right at that point, it touches the manifold exactly, briefly, but extends in a planar, linear manner off to infinity. And so this is a tangent plane to that manifold. Okay. Well, up here, that plane is going to be really far away from the manifold. But as long as we're, somewhere within infinitesimally away from that point, basically that plane is a darn good estimate for the manifold, because the more you zoom into a manifold, the more everything just gets flat. Isn't that true? That's true as long as it's continuous. If there is a discontinuity, that there could be something where no matter how far you zoom in, you never get past it. But as long as it's continuous and you zoom in far enough, a tangent plane is always a pretty good estimate for what's going on the manifold. That's the whole basis behind the extended Kalman filter, is they say, hey, the Kalman filter assumes transitions and observations and everything are linear. And we can say, yeah, that's pretty much true in the vicinity of where we are. So as long as we're only transitioning from, here to there, to there, to there, to there, as long as you take small enough steps, and as long as we're recomputing our linear tangent hyperplane at all those points before we do our math, you see how we can use a system that's fundamentally linear and just keep recomputing our tangent hyperplanes, and that'll make the whole system work. Now, it'll be off a little bit. It'll accumulate little errors every time we take a step because there's a difference between that tangent plane and the actual manifold. But presumably that difference is pretty small. And the awesome thing about the Kalman filter is it's auto-correcting, right? Because every time you make an observation, you're going to correct your state to what you really are at. Therefore, if there's a little bit of error, but this is a powerful mechanism for getting rid of errors, because it's absorbing noise in both transitions and observations, it just kind of seems like we don't really need exact precision. We just need something that's good enough so that we can stay in the realm of it, and it's going to fix itself. And that's why the extended Kalman filter is pretty awesome. Yes, it is making this bad assumption that we're going to use the tangent plane rather than the actual true manifold, because that would result in terribly complex math. But it works for gradient descent in neural networks. It works for all kinds of things. So it's a pretty decent, good assumption, and it seems to work pretty well. For your knowledge, there's something called the unscented Kalman filter, which uses Taylor series to better approximate the exact manifold of the surface upon which you're transitioning. In my opinion, that's awesome, but it seems like overkill to me for a system that's self-adapting. It seems like they're doing a whole lot of extra math to solve a problem that I don't see as being a real problem, when the real problem is something more along the lines of, well, I guess I shouldn't say what the real problem is. Whatever your problem is your problem. But I don't think it's worth the extra math. Yeah.
Also,
that's a really good argument, actually. So here's a good reason for the unscented Kalman filter. If you wanted to get from here to there, and you wanted to plan in a hierarchical manner, that is, you didn't want to just take infinitesimally small steps all the way to there, which would require a lot of computation, you may want to say, hey, I just want to first set as my sub-goal to get right there, and my next sub-goal to get there, and my final objective is to get right there. To do that, you'd need to know kind of what's going on. And the unscented filter is going to approximate it to some number. Is it second order or third order? I don't know.
you could probably go arbitrary.
I guess you can probably go arbitrary. I have to look into it. It's going to be better. It's still not going to be great. So again, that depends on how good your approximation system is. I'm guessing a lot of people would then say, hey, stop using the unscented Kalman filter. Instead, just go to particle filter. And that way we can solve it by throwing a lot of computation at it. But if you're willing to throw a lot of computation at it, why not just take baby steps all the way to your goal? I don't know. Like everything, there's trade-offs, and I think the answer is not easily apparent. If you really wanted to do long-range, big step planning, I think you'd have to actually know the equation for the whole darn manifold, and then you'd get overwhelmed by complex mathematics. I'm not sure the problem's solved. They are good at fitting manifolds.
And then you can,
I don't know. I'm not sure. I guess I'm not prepared to answer the question at this time, is what I'm going to have to fall back on. Suffice it to say, let's not do that. Let's only take baby steps, and then the extended Kalman filter is going to work really great. Okay. I need to define Jacobian matrix. Jacobian matrix. I'll give you my definition first while Wikipedia is trying to find one. If you have some function, y equals f of x, then you could say and assume y is a vector and x is a vector, right? You could fill a whole matrix with the partial derivative of y sub 1 with respect to the partial derivative of x sub 1, right? And then across one of the axes we'll vary the subscript for the y. Make that a 2, this one a 3, this one a 4. And then across another axis we can vary the subscript for the x's. So make this an x sub 2 and this an x sub 3 and pretend I updated all of those. Basically, this is a matrix of all the partial derivatives of if you change the inputs, how does that affect the outputs? And for all combinations of all inputs and all corresponding outputs. Okay, let's see what Wikipedia says. I should have done the partial of the function with respect to that, but yeah. See how on the vertical axis they've varied the subscript on the function, on the horizontal axis they varied the subscript on the inputs. And there's a really great succinct way to put it. Okay, what does this mean? This is one of those concepts that is super simple to describe and really hard to wrap your head around. What it really says is, if I change this x, how does that affect my function? Do you see that that's the same thing as, I deleted my manifold. If I moved in this horizontal direction, how does that change my position on this manifold? If f is the function of this manifold.
Well, really, that tangent plane is a Jacobian.
It is. That's another good way to put it. This tangent plane is the Jacobian. That Jacobian matrix really is this function that fits right on the plane. It's if you're right here and you take a baby step in this direction, that's changing your inputs, how does that affect your position, your vertical height on this manifold in the output direction? So that Jacobian really is exactly what we need to turn a point on this manifold into a linear function, which we can then throw into the Kalman filter. So you're going to be computing Jacobians, and then the extended Kalman filter just becomes the Kalman filter. And it turns out neural networks are differentiable, which means we can use backprop to get the Jacobians to make the whole thing work between neural networks and the system.